Hello, this is Mrs. Nearing. In this video we will be talking about rate laws and how to determine the rate law for a reaction using data. So let's first define what a rate law is. We know that rate is dependent upon concentration of reactants. When the reactants are more concentrated, there's more of them in a given space, they're more likely to bump into each other, and the more frequently they bump into each other, the greater the reaction rate, the more often a reaction will occur. We know rates also dependent upon things like temperature, which will also increase the number of collisions between reactants. And each reaction has a unique rate law, which is this chemical equation here shown in blue. It shows the relationship between rate and concentration. Notice how it's a direct relationship, so as the concentration of a reactant increases, the rate should increase. And there's also this symbol K here. K is a rate constant, and that varies with temperature. So that is how temperature comes into play with determining the rate of a reaction. When we're looking at rates, in this example, the rate is defined as the rate of disappearance of reactants. And when we talk about rates, it's in molarity per time. It could be molarity per second, molarity per minute, molarity per hour. You want to make sure you pay attention to what units might be given there. K is the rate constant. The units for the rate constant are going to vary depending on the reaction order. We'll see an example of that in a little bit. And then M and N, these are the superscripts up here. Those are known as the reaction order. So it's the reaction order just means the exponent for the reactant. So notice how our two reactants A and B, the square brackets means concentration of. So whenever you see square brackets, that means we're talking about molarity, and these reactants are going to be raised to some number that varies by reaction. That thing is called the reaction order. That's the thing we're going to be trying to figure out. How do we determine the reaction order for our reactants? And if we know the reaction order, we can write the rate law. So possible reaction orders, and remember, reaction order is the exponent in the rate law. A reactant might have any of the following reaction orders. It could be zero order, first order, or second order. So if you have a reactant, A turning into B, the rate law might be K times A to the 0, or it could be A to the 1, or A to the 2. That's what we're saying here. Those are the three possibilities for the exponent in the rate law. And these reaction orders, the exponent, cannot be predicted through the balanced chemical equation. You can't just look at an equation and say, oh yeah, the rate law is going to be this. They are dependent upon the reaction mechanism, which is something that we can't see easily, and they're determined experimentally. So we're going to look at what kind of data we might look at in order to determine the reaction order. So there's a couple of different methods for determining reaction order, and the method we're going to be looking at today is the method of initial rates. And what that means is our strategy is you're going to set up a series of experiments, and you're going to change the concentration of a reactant and observe what impact that has on the reaction rate. So if we think about what that means, let's say a reactant is zero order. That means that in the rate law, rate is proportional to, let's write that out here, that rate would be proportional to the reactant to the zero exponent. And we know that anything to the zero power is 1. So what that means is no matter what the concentration of A is, the rate is going to stay the same. So if you change the concentration of the reactant and the rate of the reaction does not change, that means that reactant is zero order. So we'll find not all reactants will actually have an impact on the initial rate of the reaction. Something can be first order. If it is first order, then if you double the concentration of reactant A, the rate of the reaction will also double. So again, if we write this out, the rate would be proportional to A to the power of 1. So like, let's say you doubled A, that means the rate would also double. If you tripled A, the rate would also triple. So if we see that happening, we know that the reaction is first order for that reactant. Okay, so we'd say A is first order. A third possibility is your reactant could be second order. And in that case, let's say you double the concentration of the reactant, you would see the rate of the reaction would quadruple. Because we're seeing here, rate is going to be proportional to so in this case, if it is second order, the rate is proportional to the concentration squared. So that means if you double the concentration, the rate is going to go up by 4 times. It's going to be 2 squared. If you triple the concentration, the rate's going to go up 9 times. So this is kind of a summary of how we're going to use this method. We're varying the initial concentration and we're seeing what impact that has on the rate. It might have no impact on the rate. That means it's 0 order. If it has the same impact on the rate, then it's first order. So like if doubling the concentration doubles the rate, you know it's first order. If it has the impact squared, I don't know how to phrase that, but like if you double the concentration, that quadruples the rate, or if you triple the concentration and it makes the rate go up by 9, that tells you that it's second order. And those are only 3 possibilities. So let's look at an example here. We've got a reaction, we got a balanced chemical equation for it, and we've got some data here below. And we want to try and find the rate law. And when someone asks you to find the rate law, basically what we're saying is first you're trying to determine the order for the reactants. So, whoops. When we're taking a look at a data set here, when you're given a big set of data, what's important is in order for our, in order for our data to mean anything, we got to make sure we're only changing one variable at a time. We want to have a controlled variable and all of the variables be controlled. So these 3 experiments we're running here, we're assuming we're running them all at the same temperature and all those things are the same. The only thing that's varying is the concentration. And if I want to know the impact that nitrogen monoxide has on the rate, I want to make sure I compare reactions 1 and 2. And why is that? Because in experiments 1 and 2, notice that the concentration of hydrogen stays the same. So what I can see here from my data is if I compare experiments 1 and 2, when I double the, let's go like this, when I double the concentration of nitrogen monoxide, it looks like my rate goes up. So it's definitely not 0 order. How much does it go up by? If you're not sure, you can plug this in your calculator. So this is 0.09 divided by 0.0225. If you plug that in your calculator, you should get something around 4. So what that means is when NO is, sorry about that. When NO is doubled, the rate goes up by 4. Therefore, NO must be second order because 2 squared is 4. If NO were 0th order, there would be no impact on the rate. So the rate would be the same in experiments 1 and 2. They'd both be 0.0225. If NO were first order, then when you doubled the concentration, the rate would double. So it would go from 0.02 to 0.04. But this time, when I doubled the concentration, the rate quadrupled, which means that NO is second order. Okay. So we know that NO is second order, so let's start filling in our rate law. So rate equals rate constant, NO squared, and then we want to figure out the reaction order for hydrogen. So now we want to look at, sorry, I keep flipping to the next slide. Now we want to look at 2 experiments in which the nitrogen monoxide stays the same, but the hydrogen changes, and that's experiments 2 and 3. So notice how in these cases NO is staying the same, but the molarity of my hydrogen is actually tripling. So when I go from experiment 3 to experiment 2, I triple the concentration of H2, and what does that do to my rate? Well, so let's think about it this way. So my hydrogen concentration, I go from 0.3 to 0.1, that is tripled. Okay, so my hydrogen concentration triples. The rate changes from 0.0075 to 0.0225. If you plug that in your calculator, you will see that that is also a tripling. So when I triple the hydrogen concentration, I also triple the rate. That tells me that the hydrogen is first order. So that is my rate law for my reaction here. So nitrogen monoxide second order, hydrogen is first order. And again, if I think through my possibilities here with hydrogen, if hydrogen were 0th order, then the rate would remain the same in experiments 2 and 3. If hydrogen were second order, then let's think about that one. Then my rate would go up by 9-fold. Okay, and neither one of those things happened, so it turns out that it is actually first order. So if I triple the concentration, it triples the rate. The other thing you want to be able to do with this is you want to be able to find the value of the rate constant with appropriate units. So right now I have a generic rate law written. I just have a generic K in there, I should say. I don't know the value of K, but you can solve for the value of K by just rearranging this equation and solving it for K equals rate divided by NO squared divided by H2. And where you get these numbers from is you just pick an experiment up here at the top. So just pick one row, like experiment number 1, plug in the rate, plug in the values here, and when you're plugging those numbers in, make sure you're paying attention to units so you can figure out what the units of K are, because the units of K are going to vary based upon the reaction order you're looking at here. So here's our rate law. So you can see NO is second order, H2 is first order, and if we look over here, in order to solve for the value of K, I can rearrange this equation to solve for K. I'm going to plug in some numbers from my data table, and when I do that and I pay attention to units, notice I will end up with molarity per second divided by molarity squared times molarity. So one of those molarities cancels out, and what you're left with is 1 over molarity squared times second. Another way of writing that is molarity -2 second -1. That just means the inverse of the molarity squared. So you could write it this way or this way, either one is fine. And again, it's important to keep in mind with figuring out the units of K, you don't memorize it. It's not something you memorize. It's something that you look at your data and you plug the numbers in and you pay attention to the units and you see what that gives you. So take a look at what cancels out. There's another example here for you to try, and you can check your work right here. And there's 2 more videos that you can look at that have other examples to work through. All right. Please email me if you have any questions.